Hello everyone, in this video session we are going to talk about the position of the peak in NMR spectrum, and we'll see what information we can have from the position of the peak to interpret the NMR spectrum. So in our previous lecture we have seen that ethyl acetate has three different type of protons, so that's why it giving three different signal in the proton NMR. But now question here, why these all protons coming at different positions? And why this peaks at higher frequency and this peak at lower frequency? Because this side we have high frequency in NMR spectrum, this side we have low frequency. As we know, the gap between two energy states decides how much frequency a proton requires to get resonate. But if we see, we are applying same magnetic field here for all type of protons because they are in same molecules. The magneto-gyric ratio is also same. So there is some other factor, those are changing this gap between protons, so that's why they are coming at a different resonance frequency. But if you see here, the value on x-axis are not written in frequency or magnetic field units, which we were talking earlier. It's written in ppm, that's a chemical shift value, and we will discuss that also, that why it is written in chemical shift value, not in frequency or magnetic field units. And so now come back to our question, why all three signals come at different position in the proton NMR of ethyl acetate. So now each nucleus is surrounded by electrons, those are also charged particles, and in the presence of applied field, that is B0, these surrounding electrons start to circulate around the nucleus, and so they generate a secondary magnetic field called induced magnetic field, which is Bi, which opposes the applied magnetic field in the region of the nucleus. So this is the applied field and this is the induced field, which is in opposite direction of the applied field, means it is opposing to the applied field. As a result, the field experienced by the nuclei is not quite the same as the applied field because this induced field opposing to the applied field. So whatever field our nucleus will experience will be different than what we have applied here. So we can say the actual field experienced by nuclei will be applied field minus induced field. So the electrons are said to shield the nucleus from applied magnetic field. So this condition is known as shielding of the nucleus by the electrons. Now we have to put this information in a flow chart. So we'll see the higher the electron density around the proton, the higher the shielding of the nucleus by electrons. Higher the shielding, higher the induced field, and lower the field experienced by nucleus because we know this opposing the applied field, so lower the frequency required for resonance. NMR of ethyl acetate, the induced magnetic field is different due to different chemical environment, so different type of protons will resonate at different frequency and will come at different position. So that's the answer of our question here. So now in this spectrum we can say this side is high frequency side, this is a low frequency, or this is de-shielding side, this is a shielding side, because de-shielding means less electrons around the nucleus, less the induced field, or higher the field experienced by the nucleus, or we will say down field and this side is up field. Now the resonance frequency depends on the gap between two spin states, as we have discussed earlier, and the gap will depend on actual field experienced by a nucleus. So actual field experienced by a nucleus or the gap between energy states will depend on applied field as well as on induced magnetic field. So now applied field is fixed because we are using same instrument for molecule. Gyro-magnetic ratio is also fixed for a nucleus because we are considering only proton here. The only factor that can change the induced magnetic field and overall will affect the resonance frequency or chemical shift value for chemical equivalent protons. So now we are introducing one new terms, that is a chemical shift here, and we will see what is chemical shift value. So as we know, this side is high frequency, this side is low frequency. and this is not written in a frequency unit or magnetic field unit. This is written in ppm. That's a chemical shift value. So we can say this side is high chemical shift value and this side is a lower chemical shift value. But why we do need chemical shift scale instead of frequency or magnetic field? The frequency at which a proton resonates mainly depends on the applied magnetic field because it affects the gap between two spin states. It means if we run a NMR sample on various machines working at different magnetic field, the resonance frequency for a set of proton will be different at different magnetic field. So since at higher magnetic field a proton will resonate at higher frequency, while at a lower magnetic field same proton will resonate at lower frequency. So because you know the gap depend on the applied magnetic field. So it will make to the NMR spectroscopy very difficult if we could not say where our proton will appear in the NMR spectrum, because whenever you are using different machine you will get different position for same proton. So that will make it very difficult to predict or to interpret the NMR spectrum. So to solve this problem, we use a reference compound each time and say how far a proton in sample resonate from the protons of reference compound. And it will make life easier because no matter what the operating magnetic field of the NMR machine, the signal in the given sample will always occur at the same resonance frequency from the resonance frequency of reference compound. Because now we will just consider the distance from the proton of reference compound. So here we have to remember this in everyday life rather than actually referring an NMR machine in the strength of the magnetic field in Tesla or other units. We usually just refer to its operating frequency. For example, 9.4 Tesla NMR machine is referred to as 400 MHz spectrometer because you never hear that this instrument is 9.4 Tesla or this is 1.4 Tesla. You always hear about this is 500 MHz instrument, this is 4 MHz instrument. So means that's the operating frequency of that instrument. Since that is the frequency in this strength field at which the protons of the reference sample resonate. So we know all the protons resonate at approximately at the same frequency because the difference in the gap between spin states is very small. However, the exact frequency depends on the induced magnetic field because it's very small, so that will make very little change in the gap between two energy states for different protons. As a result, the nearby frequency of the operating frequency will be sufficient to resonate the sample protons. Means if we are using 400 MHz frequency to resonate the protons of your sample compound or your reference compound, then nearby frequencies of 400 MHz will be sufficient to resonate the proton of your sample. So now what reference compound we use in NMR generally? So we use generally TMS or tetramethylsilane in NMR spectroscopy. So all the 4 methyl groups, that is these 4 methyl groups in TMS are chemical equivalent. So all 12 protons will be chemical equivalent in TMS. So they will give only one signal. And silicon is more electropositive than carbon. So proton in TMS are fairly shielded. And we will see why they are shielded, because we didn't consider yet those points make it shielded or de-shielded. It means they resonate at a frequency a little less than that of organic compound. Means TMS will be require less frequency than mostly organic compounds. So it will come before than other organic compounds. So it means our reference sample will not interfere in the middle of our spectrum, and it is not involved in intramolecular association with the sample or solvent, hence the absorption position of its proton remain unchanged. It is soluble in most of the organic liquids. So now we will say 400 MHz NMR machine means the operating frequency at 1.9 Tesla to resonate the protons of TMS. So chemical shift value is the distance of signal in ppm from the signal of TMS. Means this is the distance of these protons from TMS. This chemical shift value is the distance for this proton from the TMS proton, and this is the distance of this signal from the TMS signal. So actually chemical shift is the distance from the signal of TMS protons in ppm or parts per million. So here we will see that the horizontal axis is actually frequency, but usually quoted in ppm. So for example, if we use 100 megahertz NMR machine, then 1 ppm will be 100 hertz. Means this 1 ppm corresponds to 100 hertz in a 100 megahertz machine. So in above given spectrum, CST protons give a signal at 1.8 ppm at 100 megahertz, means they resonate at 180 hertz higher frequency than the proton of TMS. So means this distance is corresponding to 180 hertz higher frequency than the proton of TMS. So this is the formula to calculate the chemical shift value. So chemical shift in hertz from TMS protons multiplied by 10 to the power 6 divided by the operating frequency in hertz. So we can see with some example, a peak at 60 Hz from TMS at an applied frequency 60 MHz would be at 1 ppm. So the same peak at an applied frequency of 100 MHz would be at 100 Hz, and it will be equal to 1 ppm. So 1 ppm in 60 MHz machine we can calculate by applying this formula. So the shifting is 60 Hz. We are using 60 MHz instrument. When we will put this value here, we are getting is 1 ppm. Same value if we use 100 megahertz instrument, we are getting again 1 ppm. So this shows that 1 ppm is equivalent in all megahertz instrument. So whatever is the operating frequency, but the distance will be from TMS proton, for our sample protons will be always same. So this showed whatever the operating frequency, signal will appear at same chemical shift value. It will never change whatever your instrument or whatever your operating frequency. So when you change from one machine to another, let's say from a 200 megahertz to 500 megahertz NMR machine, chemical shift value stay the same in ppm. So it never change whatever the applied field. So thank you very much and have a very nice day.